Okay, I'd like to welcome everyone back to the conference. I'm Professor Alison Keeley, and I am the Research Capability Coordinator for the SmartSat CRC. This is a very exciting session we're going to enter because we're going to hear from our next generation of space experts. The SmartSat CRC has committed to providing something like 72 PhD students, and over 30 have already been committed. Their topics broadly cover many areas of the CRC's strategic and priority research areas, everything from space IoT comms to AI-powered autonomous systems in space. The really exciting aspect of what the research does is that it connects to the industry partners and supports the practical application of the proposed thesis topics. This really demonstrates SmartSat's commitment to growing and fostering Australia's space industry, building strong linkages between academia and industry, and opening up opportunities for innovation across industry. This afternoon, we are really honored to meet a few of our PhD students and hear about their research and discuss more openly how industry can engage with them and look at how to build their professional development. You should know that poster presentations from these students and others who are not actually here to present can be viewed in the exhibition hall throughout the conference. And I really encourage you, if you get an opportunity, to go and have a look at the exciting work that our PhD community are investing in. I would now like to introduce Professor Wei Zhang, who is the SmartSat Higher Degree by Research Director. And please remember during this session to ask questions via the Q&A functions and during the Q&A session. Enjoy the session. Over to you, Wei.
Yeah, and welcome, all the attendees to the conference, the SmartSat Conference 2021. As Alison said, I'm the HDR director of the SmartSat. So my role is to managing around 72 PhD students. SmartSat is going to educating. And one of the things we do slightly different is from a normal university PhD student is that at SmartSat, we're proud of nearly all of PhD students are strongly connected with the industry. Most of them topic, if not all of them, are strongly linked with industry partner. Partner is coming on board or provide very strong support in terms of data sets, equipment, experimental help. And by doing this, we are hoping, so our PhD students will have a strong industry skill sets and helping industry solving the real world problems. And for this, and we are going to educating the new generation of Australian space industry workforce. So in the following, you will have the opportunity to hear our altogether our non-presenters. Their topic is spanning all over from AI and machine learning for the space industry, advanced comms technology for space industry, remote sensing and IoT technology for the space, and many others. And I would like to take this opportunity, to send out a message to our attendees from both academic and industry. If you're an industry attendee, I'll put up a poll question. So please let us know which area you're interested in terms of supporting SmartSat PhD students, because we still got quite a few places available which we can place the PhD students to help to grow the technology at your company. So please let us know whether you're interested and which area you're interested. And also for the academic attendees, please let us know whether you're interested working with our industry partner to develop industry-driven research proposal. Or maybe you may be thinking, oh, I'm interested, but I don't have time. And let us know as well, because we can help you to bridge the gap. We can introducing industry partner to you so that you can work with your partner with minimum amount of time in developing real world industry-driven projects. Okay, so without further ado, just some housekeeping matters. This session will be divided into two parts. So in the first part of the PhD session, we'll be hearing from 5 presenters. And after break, 10 minutes break, and there will be 4 more presentations for the second lot. For each presentation, most of them recorded, and except we do have one live presenter. And so presentation itself is about 10 minutes and plus 5 minutes Q&A. So I hope you can enjoy it. So I'm proud to present to you our first speaker, Jordan Plotnick from University of South Australia. So the topic, and he's going to present, is space system resilience. So Jordan received a Bachelor of Engineering degree with first-class honors in telecommunication and network engineering from Swinburne University of Technology, Melbourne, in 2013. And he's currently pursuing his PhD studies under supervision of Professor Joe Slay at the University of South Australia. And his research interests are centered around cyber, physical conflict, emerging threats, and resilience. Over to you, Jordan. Thank you.
Hi, everyone. My name's Zach. I'm a PhD student from La Trobe University. I'm going to be talking about how we can use
So I believe I've got one of the after lunch slots here. So just hang in there. My presentation won't take long. Good afternoon, everyone. My name is Jordan Plotnick. I'm a researcher at the University of South Australia, a PhD candidate, and I'm on a SmartSat CRC scholarship. I'm very excited to be here today as part of the SmartSat CRC conference. This new hybrid way of doing things, I think, is the way of the future, and well, very much the way of the present, in fact. So I believe I've got one of the after lunch slots here. So just hang in there. My presentation won't take long. I'll be talking today about some of the research that I've been doing with SmartSat CRC, which is around space systems resilience. So as you're all probably very well aware, space systems are a vital critical infrastructure. And that makes them a bit of a target, in fact, quite a target. Alongside this rapid development of space that we're witnessing right now in the industry, cyber attacks are increasing in frequency and sophistication. The exploits that are available range from the opportunistic bored teenager or someone trying to get a bit of cred, go out there and make some impact on critical infrastructure or leave a bit of a mark, all the way through to complex and persistent threats, namely from nation states, organized crime, people with a lot of resources and a high motivation. This rapid commercialization of space that we've been witnessing has resulted in global supply chains, so really complex supply chains, layers and layers of different collaborating organizations that span the globe. And most of these are privately held. And on top of this, we're seeing a deployment of a lot of emerging technologies into new satellites that are being launched. This includes the Internet of Things, artificial intelligence, among a bunch of other different areas. On top of that, there's a lack of security regulation and standards currently for the space sector. This is actually quite global, but especially in Australia. So that has led to, alongside all of these technologies, which we may not even necessarily know how to secure yet, there's also the lack of oversight, which is increasing vulnerability and the attack surface of satellites and satellite constellations. So the goal of this research is is to actually look into resilience, which is a key aspect of critical infrastructure protection, not just for space systems, but you'll see resilience being talked about as a bit of a hot topic across the critical infrastructure sectors, especially in the energy sector. There's some quite progressed research on this topic. However, for space systems, the idea of resilience and in fact space security, space system security is yet to be defined or understood to a better level. So the goal of this research, I'm researching myself under the supervision of Professor Jill Slay at the University of South Australia. And we've got four main goals here. One is to scope the domain of space system security. Who's involved, how big is it, what does it actually entail? Second is to define space systems resilience, which is what this presentation will be focusing on. I'm limited to 10 minutes here, so I don't want to bore you with all the things here, but if you are interested, you can reach out to me or ask any questions after this. The final two, developing a pragmatic resilience framework and testing that framework against a conceptual model. These are still in progress, so they're undergoing, but are well on their way. In terms of space system security, just to give you a quick overview, based on the literature search, there are three dimensions within space security. So it's primarily previously understood as a military domain, resulting from the Cold War especially. However, these days, these three dimensions are commonly understood. So there's security in space, security from space, and space for security. Security in space is going to be the point of this research and this discussion here, so I'll skip over that for now. Security from space is talking about protecting Earth from space-based threats, such as asteroids and other things like that. And space for security is your military space operations, using, among other things, it's not just exclusive to military these days, but it's using space for your security operations. Primarily military. So space systems security specifically is concerned only with point number one. So that's what we'll be focusing on here, achieving security for your systems that operate in space. And that includes your supporting ground systems and telecommunications infrastructure as well. So resilience is a function of the space system security domain. It's an aspect of security, and we'll delve into that some more right now. According to the research that we've done so far, and there are some published papers if you're interested to see a bit more of the workings behind this, happy to answer any questions again, but I'll read through this here. So space systems resilience is the recurring ability of a space system, including all subcomponents and supporting functions, to anticipate, survive, sustain, recover from, and adapt to high impact, low frequency events. Now, there are a lot of specific words there, so let's delve a little bit deeper. Perhaps the first thing that comes to mind is why just high impact, low frequency events? Why shouldn't a space system be resilient to all types of security events? Well, good question. There is a difference between resilience, risk, and reliability. And without spending too much time on this, given the time constraints, I've drawn up a bit of a diagram here. So this is, you may be familiar with it's based on the standard kind of risk matrix. So you've got your frequency or your likelihood up the top, and then going across is your impact from low to high, or your consequences, also commonly known as. So if you've got a low frequency and a low impact event, so something that happens often and it doesn't cause much duress, that's generally more of a reliability function. So reliability engineers take into account all of these things. They're generally predictable events because they occur frequently, and the impact isn't too severe. So you're just trying to keep the system kind of operating. That's a basic operational requirement. When you cross from the top left quadrant to the bottom right quadrant, you're looking at low frequency, high impact. And that's where your resilience comes in. So resilience is primarily concerned with your things that don't happen very often, often referred to as black swan events or gray swan. However, when they do happen, it has a large impact. And then the other two quadrants are, if you've got high frequency, high impact, it's happening often and it's having a huge impact. That's an unacceptable risk. You probably won't be operating for very long. Low frequency, low impact, generally an acceptable risk. These are very broad because it all has to align with the organizational risk maturity model and risk acceptance model. So moving on, accepting that it's high impact, low frequency events, we're looking now at the resilience cycle. So these are those keywords that a system has to be able to achieve to be called resilient. And there are levels of resilience as well. So you've got the high impact, low frequency security event coming in there from the right, and that immediately knocks you into survive mode. So your system, your space system, should be able to anticipate some kind of event. In fact, anticipating an event that you may not have occurred. So just being prepared for your security and your defenses to be breached. And then you immediately jump into this survive mode. How do you survive this event? How you're going to absorb the shocks and make sure that it doesn't knock out your operations completely. Once you've managed the survive phase, you move into sustain, which is sustaining your baseline operations. So to have a resilient system, no matter what your impact is that comes in, you should be able to sustain your core operations. After you've kind of moved through that stage, you're then looking at recovery. And some of these can happen concurrently as well. So recovery, I think, is quite self-explanatory. It's about bouncing back from that event. Often people use the word bounce back for resilience. However, that is one aspect of resilience. And then the final piece here is your adaptation. So adapting to what you've learned from this event. It was low frequency, so you've most likely learned something, and then actually making some changes, whether it be technological or procedural or something to do with your personnel or your organizational structure. It's making changes to be able to better anticipate events in the future. And then whatever's left over will be your residual risk, which it goes out into the environment and also comes back to the system. So your system will have to withstand some risk usually. And then often a cybersecurity event will have other kind of impacts onto other environments. So say if it's malware or something like that, it can go out, it can spread. So I understand that this was pretty short, but just wanted to give you a quick run through of the research that we've been conducting. And thank you for your time. And if you have any questions, I'm free here, or you can contact me by this email. Thank you.
Hi, Jordan. Yeah, thank you very much for the very interesting presentation by Jordan. Yeah, our first student speaker. Yeah, and the talk is quite interesting. Yeah, space system resilience. And I would like to invite any questions from the audience if there is. Yeah, for those of you are interested in asking a question, there's a live Q&A, the panel where you can type in the questions, and our presenter will answer that question live. While we're waiting for people, typing the questions, Jordan, just got a question to ask you. Yeah, like I said in the beginning, yeah. So SmartSat PhD, we are taking a slightly different, as most a PhD student at a traditional normal university environment, which focus more on academic research. But we are very much adamant in encouraging our students to engage with the industry. So in your experience, I would like to you share with us your experience. How do you find, working with your industry partner? What kinds of help they're giving you to support your advance in this, in space system resilience?
Thanks, Wei. Excuse me. Thanks, Wei. Yeah, that's a good question. It's interesting. It's an interesting question, particularly because I've actually changed industry partners throughout my my PhD here. So I started off with Thales, and I got some really good support from them. They were very encouraging, very active, and the research was mutually beneficial both for them and for me and for SmartSat. So it was very good. Now I'm in a bit of a unique position because I've actually started my own company, which is kind of sponsoring it as well. So that's been it's been really good, honestly, working with SmartSat throughout this PhD. I've had a lot of opportunities, and it's been really interesting to get some real world problems through both the networks and the different opportunities that get presented to SmartSat to be able to work on.
Excellent. Yeah. So good to hear that you are having your own company, and hopefully this journey helped you a little bit in informing up your own staff. Now we got some questions, interesting for questions from the audience. The first one is, what are your thoughts on quantifying resilience in space?
That's a very that's a very good question. Quantifying resilience is it's a problem that's been around for some time. So my approach to resilience is primarily, it's similar to a risk-based approach, where it's less quantified in kind of scientific terms, and a bit more of an assessment based on our perceived levels of threat, and our understanding of historical events, of which there are only so many that have occurred so far. So yeah, that's the approach that I'd recommend, is much more like that. So you come in, you look at the different kind of phases of this resilience, which can occur concurrently, and then taking into account the different security countermeasures that have been put into place, as well as operational needs and mission requirements. Then you can come to a bit more to a bit of a soft kind of answer to that question. For the moment, there is a lot of work going on more scientific approaches, I should say. However, it does get complex, especially in a space environment where a number of systems are entirely unique, and quite niche, and so it can be difficult to apply this concept of resilience, which is both system specific and threat specific, broadly. But there is some work going on in that still.
Excellent. Yeah. So next question is, how big impact does the type of the payload operation have on the risk profile for resilience engineering?
As in, sorry, I just need to clarify that question. Is the person asking this interested in how the actual payload of the satellite comes into the resilience equation? Is that what we're asking about here?
Yeah. I think that is my understanding of the question. Yeah.
Okay. Yeah. Yes. So I think that it's a really big part, because the payload will often be quite related to the mission, and what's actually being trying to achieve, what you're actually trying to achieve with the system. And at the end of the day, resilience is about resilience to that mission itself. So the payload is integral to that. A lot of other aspects of space systems, can be sort of copied from one part. Say if you're launching a satellite, like your launch infrastructure will probably be quite similar from launch to launch. Whereas when it comes to payload, that's exactly where the question of security and resilience is particularly interested, given that it's usually quite related to the mission. Yeah.
Thanks, Jordan. Yeah, we have a last question, but not the least. So this question is from our CRO, Carl. Yeah, Carl has a very interesting question to ask you. So could you use Aurora? Do you think you can use Aurora distributed flat satellite to demonstrate your approach?
The Aurora space cluster, is that what we're talking about?
Yeah, Aurora distributed flat satellite. Yeah. Yeah. I mean, can we use that to test? That's the question? Yeah, that's right. That equals back in, what I just said at the beginning. Yeah, we won't like to you guys working closely with the industry. So having demonstrate whatever you do with the industry, a real system, I think that's the way we show the impact.
Yes, 100%, most definitely. And there actually are some. We're looking at some use cases right now, some really interesting use cases about where this can be applied. And one of the things that we're actually part of the testing that we're doing right now, we're getting towards the end of the thesis, and we're reaching out to a number of different experts in the industry, both in literal industry and in academia and in government, and getting feedback on this model and on the approach, based on their own operations and what they would use this framework for. And then after that, we'll have a much better understanding of how the framework can be applied, and also across the different problem areas. So if we're looking at a macro kind of satellite constellation versus a micro, perhaps just the launcher vehicle. So these are all questions that we're looking at now. And the Aurora Space Cluster, 100%, that would be that presents a fantastic opportunity with real world systems and real industry partners who are actively interested in solving some of these problems in the space sector, of which I firmly believe security is a fundamental component to that. So yes.
Thank you once again, Jordan, for both your interesting question as well as answering the conference attendees' questions, and you've done well. Thank you.
Thanks very much, Wei.
Yeah. So our next second speaker is Anne Battens from University of Sydney. So I believe she will be presenting live. So her topic is about autonomous navigation of satellites for space exploration. So Anne holds her professional master's degree in aerospace engineering from University of Sydney and is currently pursuing her PhD in the same fields. And her present research focuses on vision-based autonomous navigation of robotic craft for space exploration. Anne earned her undergraduate degree in mechanical engineering at the University of South Western Australia. And since then, she's been working as a private in a helicopter company and hope to achieve her commercial pilot's license. And she's very passionate about STEM education and is actively involved in many outreach programs. Over to you, Anne.
Thank you very much. Hello, everybody. As I've been introduced, I'm Anne Battens from the University of Sydney. I'm a SmartSat CRC scholarship recipient in partnership with Thales Australia. So I'll be presenting to you today on autonomous navigation of satellites for space. So a little bit of background. So autonomous navigation in space, it's pretty useful. Robotic platforms are required for deep space missions. So when we're sort of looking at going further into space, we sort of run into difficulties with having humans in the loop and lag and that sort of thing. So that's why it's pretty essential to be able to have these autonomous robotic platforms. Additionally, a high level of safety and reliability is required for autonomous robotic missions. So I guess kind of linking into what Jordan's already presented on earlier today. So we need that so we're not sort of adding any additional problems to space that we might encounter. Typically speaking, when we sort of start to look at the literature for this sort of application, vision-based approaches are the current industry trend, and particularly when we're looking at sort of close proximity operations, which I'll sort of be discussing and presenting to you a little bit today. So autonomous navigation, in terms of the context in what we're looking for in a space environment, it has many applications. Useful ones that are sort of relevant to, I guess, the SmartSat sort of research areas as well are space domain awareness. So ensuring that we're encompassing what is happening in sort of space situational awareness and space domain awareness. It's very important to be able to do that autonomously as well. Additionally, if we want to look at in-orbit servicing of satellites and spacecraft and those sorts of things, so whether that's refueling or removal of space debris. So quite a few different applications that we can draw on there, and it's, I guess it can be applied more generally as well. So navigation as a whole sort of encompasses quite a lot of different areas. So when sort of in the context of what I'm looking at with respect to space robotics and space navigation, we sort of first want to identify the object, so object detection, and then to be able to identify it. So basically seeing an object and then saying, okay, what am I looking at? What is this in reference to my library of knowledge, or how can I categorize this? From there, we kind of want to look at pose estimation. So estimating, basically the orientation of the spacecraft, which is kind of what I've been sort of delving deeply into at the moment. And then from there, we want to look at sort of tracking an object, and that kind of ties in with that space domain awareness and space situational awareness as well. And then once we're tracking it, having some way of sort of localizing and mapping and storing that information to then be able to go on and say, interface with that spacecraft or that satellite, or to be able to perform in-orbit servicing or debris removal or whatever it may be that's relevant at the time. But this is sort of, I guess, the umbrella and how I sort of see it for my current area of research. So as I've said, at the moment, I'm sort of really diving deeply into the pose estimation. So pose estimation of an object in a general sense is the relative position and orientation of that with respect to some reference frame predefined. So whether that reference frame is Earth or with respect to, say, the observation spacecraft. A pose can be extracted from images using computer vision techniques. And that's sort of, I guess, the more traditional sense of how we sort of do pose estimation using vision-based techniques. And as I've kind of mentioned, so once we've acquired a pose, we can then begin to do things such as tracking and navigation, do some more exciting things like space debris removal or inspecting objects or interfacing with them for in-orbit servicing and those sorts of things. So when we're looking at pose estimation of non-cooperative satellites, and what I mean by a non-cooperative satellite is, say, a piece of space debris, or perhaps it's a satellite, a spacecraft that needs servicing in orbit that's not necessarily set up to do that. So what I mean by that is perhaps it's not communicating correctly, perhaps it's sort of tumbling, we don't know enough information about it, or perhaps it's not necessarily prepared in the sense to perform in-orbit servicing. So there's kind of some challenges that come along with that. So especially if it is non-prepared and we essentially don't know much about the object that we're going to be surveying, we may not have, say, predefined models of what this is. So whether that's just the physical geometry or other information, which is not necessarily a bad thing in the context of this research, because model-based approaches are very computationally intense anyways. So, which is why there's kind of the benefits, I guess, of doing this sort of more general approach, and that you're not necessarily relying on a predefined model and that predefined knowledge. Additionally, when we're using sort of vision-based techniques, the Earth in the background can act as a cluttered scene, which is not really ideal for the computer vision techniques. So we do need to do sort of some pre-processing and those sorts of things of the images. Additionally, in space, the sun's not always in the right position to get a nice selfie of an object. So we do have some difficulties in illumination conditions and those sorts of things as well. From there as well, representing pose in 3D space. It's a very, very big problem. I mean, space is quite large, it's multidimensional, and representing that in a continuous and non-linear manner presents its own challenges, which I'll touch on a little bit later. Additionally, as I've said, if we're using sort of non-cooperative and non-prepared spacecraft, we cannot rely on those predetermined visual features or markers. So perhaps, the spacecraft's not necessarily set up to be observed correctly. So, we might not be able to rely on those sorts of things that we would if we had, let's say, testing something on the ground. So the solution, using neural networks is kind of what I'm proposing, or what has also been proposed by some other literature as well, to perform this pose estimation. So in terms of what neural networks are and how they kind of just relate, a little bit of an overview here. So deep learning is a machine learning technique that learns features. So in this case, I'm asking it to learn some information from images. Data it requires labels that sort of describe the desired output. So in this case, it's whether I want to, so we're looking for a pose based on an image. And then this kind of model, generally, it's made up of lots of different layers, and that sort of is what generates a neural network. So in terms of simulation and sort of how I've been testing this sort of thing, I should mention that this simulation is provided by Thales Alenia. So they're using their software here called the SpyCam. So basically, we'll be simulating an image of a satellite, say, rotating in space, or whether we have a camera model that orbits around this spacecraft. This simulation is pretty good because it has lots of different dynamics and illumination conditions already built into it. So from this, I'm able to basically get a very big image data set and provide the correct pose is essentially the pose that we're trying to teach the neural network. So use that leveraging that machine learning techniques to then be able to estimate the pose. So some preliminary results. So basically at the moment, we're currently achieving about 5 degrees accuracy when looking at a satellite in close proximity while it's rotating. So from that 5 degrees accuracy, by using some kind of other navigation techniques such as applying Kalman filters, we can also kind of benefit from the dynamics that we the dynamic information that we get to do that sort of Kalman filtering. So that's pretty exciting stuff. So using basically the neural network to estimate the pose, and then that pose essentially acts as an observation, which then goes into a Kalman filter. In terms of future work, so ideally we'll be training the neural network on more of a wider variety of images. So the neural networks and the models aren't learning very specific simulated scenarios. So I've got a couple of different other simulations and a couple of different other satellites and spacecrafts to teach these neural networks. So hopefully using some transfer learning and the benefits of that too. From there, it's pretty exciting to compare this sort of neural network method to traditional feature detection methods. So I've kind of mentioned a few that there's some kind of predetermined sort of vision-based techniques for pose estimation. So comparing those and seeing, obviously, computationally, neural networks are intense to train, but once they're trained, doing sort of comparisons of that to then determine how this will be able to behave on board. Additionally, so spacecrafts tend to be square. So there's some pretty exciting investigation going on to sort of the symmetry domain analysis, and that's sort of where I'm kind of diving deeply into the world of Kalman filtering as well to sort of hopefully overcome some of those challenges. And then as well, testing this pose estimation and other components of navigation, so sort of that tracking and that sort of thing that I've mentioned, on a satellite testbed that we've got at the University of Sydney. So being able to actually perform some experimentation, so it's not just a sort of simulation-based thesis, essentially. So that's pretty much it from me for today. So yeah, I'd like to thank you, Thales, for their help in this project, and thank you for your time. I'll answer any questions now.
Yeah, very interesting topic. I would say, computer vision is one of the fastest growing, area in the world, perhaps, because I did a CVPR submission last night. It was the entire system was crashed because too many, submissions simultaneously. Yeah, and I congratulate you on to the space domain and on finding your presentation. Yeah, here we have a question from the audience. Is what prior information is practical and beneficial to have on board to do identification and then pose estimation? And what are you using at the moment to get range information from the optical images?
So they're both some really good questions. So in an ideal world, I'd be able to use sort of the trained neural network to then be able to approach any spacecraft in the general sense of a model to not necessarily require any prior information or identification. Ideally, when we're sort of doing in-orbit servicing, you'd like to think that you know what you're approaching. So having some kind of information as to like this, for example, this is a kind of a catalog almost of spacecrafts that I've got. I know that I'm approaching this one, and then that will be able to give a more accurate pose. So hopefully that answered the question. Just repeat the second question that was asked in that.
The second question is about what are you using to get range information from optical images?
Mm-hmm. So at the moment, I'm currently just inputting the range into the neural network. So as I said, sort of doing some simulations at the moment. However, I'm currently looking as well at fusing other data information in. So whether that be LiDAR information and fusing that with a vision-based technique, or as well looking at, say, example, feature point extraction, and then putting that as an input into the neural network to then combine that range information. So then we can get that relative pose rather than just, so we can get an absolute pose rather than just a relative pose information.
And yeah, I happen to have a question on myself to ask you. Yeah, you probably can share with us. Deep learning has been used very widely in computer vision. Yeah, in the past, I would say, at least a decade or two. So
Yes.
previously, I think people have been using convolutional neural networks have been extremely success in computer vision, but maybe 2 years ago, I think suddenly this transformer neural networks comes up. And now it becomes key. So I wonder, what specific neural networks are you looking at for solving your vision-based autonomous navigation problem?
That's also a really good question. So I'm also currently sort of in parallel testing different neural networks on the go. So it depends sort of on the data set as to with, and as well, I should mention that there's sort of two different approaches to the sort of neural networks, or I guess machine learning in general, is you can treat it as a classification problem or a regression problem. So for example, if I'm just wanting to say classify images in a very coarse manner, I can treat this as a classification problem, so can kind of leverage that. Whereas ideally, I'd be able to detect this regression sort of domain of the whole spacecraft and the whole possible pose solution. So that's leveraging different regression neural networks. So I'm currently investigating using the most simple neural network to say, like, okay, if I just have really bare bones, really try and make it essentially really efficient, and what accuracy can we achieve? And then in combination with other sort of inputs and other navigation things, is this okay to say, for example, if I achieve an accuracy of 10% using a very small, very thin layered neural network, is that acceptable when applying a Kalman filter and doing other fault detection versus doing one with many layers? And for example, I've even tried using ResNet with multiple a very deep and intense neural network to see what kind of a comparison it is there. So hopefully I can give like a good solution that sort of benefits both, I guess. So hopefully that answered your question.
Yep. Well, sorry. Yeah. So one audience just retracted. And then putting the question back. Yeah. So we have one final question for you. So have you considered combining neural network with Kalman filter?
Yeah. So that's also kind of one of my sort of areas of research as well. So kind of a little thing on the side is, at the moment, it's sort of training the neural network, estimating the pose, and then putting that into a Kalman filter. But I'm definitely experimenting with sort of incorporating them together and seeing if we can do that sort of thing. So yes, is the short answer.
Yeah, I suppose the audience is asking whether you can use a Kalman filter or something similar for doing the pre-processing. Yeah, so that you can feed better information to your neural networks. Yeah. Anyway, I find your presentation addressing one of the hottest topic and apply that to the space domain. Very interesting, very entertaining. And thank you very much for answering the question for the audience.
Thank you.
And we our next presenter is Mahat Shibata from University of Adelaide. So his topic is about the potentials and limitations of the IEEE 802 15.3D standards for terahertz satellites. So the Mohammed Shibata complete the Bachelor of Science and a Master of Science degrees in Electronics and Communication Technology from Al Azhar University in Cairo, Egypt, in both 2006 and 2012, respectively. And he received Adelaide International Scholarship back in 2018. And then he joined the School for Electronic Engineering at University of Adelaide. Now he's currently working towards his PhD on terahertz communication. Now, his current research interests including but not limited to terahertz communication, terahertz photonics, and microwave photonics and radio over fiber RF system. For those of you are familiar with communication, so in the 5G standard, the millimeter wave band has been very popular, and in the next generation, the so-called 6G mobile phone system, and looks like the terahertz communication will be our standard. So this is a very, very hot topic at the moment. I think the industry working closely around the globe with the academic university researchers to advance this field. So we'll be hearing something interesting about this topic. Over to you. Thank you.
Hello and welcome to the SmartSat conference. My name is Mohammed Shahata and my project investigates the potentials and limitations of the IEEE 802.15.3D standard for terahertz satellite communications. This project is supervised by Professor Witherwatt, the founder and leader of the Terahertz Engineering Laboratory in the School of Electrical and Electronic Engineering at the University of Adelaide. Also, the project is co-supervised by Dr. Key Desmond Wang from the School of Engineering at RMIT University. This presentation is going to be divided into 4 major parts. First, I'm going to give a very brief introduction before I overview the project framework. After that, I'm going to focus on some selected research outcomes before the talk is finally summarized and concluded. So let's begin with the introduction. It is foreseen that tomorrow's telecommunications networks will be able to host a wide range of high-speed wireless services. Also, satellites are expected to play a very important role as relay nodes in these networks. But currently, the frequency allocation plan is fully booked up to 100 gigahertz. So, to account for the massive waves of data traffic expected to hit our infrastructure in the next few years, we have no choice but to go beyond 100 gigahertz, or technically speaking, the terahertz window. That part of the spectrum which extends from 100 gigahertz to about 10 terahertz, which is the next available step where we can put our feet in such a congested spectrum. But how about employing the terahertz technology to satellite communications? Is it just a nice proposal with no guarantee of success? The answer is no, quite the opposite. It's doable, especially after the first satellite was sent up last November for the first test of terahertz satellite communications. And like any other communications network, routing signals over satellite networks needs to be regulated by globally adopted standards. As an example, in 2002, in what was so-called the Cisco router in low Earth orbit, or the CLEO project, a Cisco mobile access node was mounted on a satellite to verify the feasibility of using commercially available components for space-based communications. What's more, subsequent efforts have been reported to demonstrate the possibility of operating these originally home-based equipment using terrestrial wireless standards. And these standards actually include the IEEE 802.16 standard, which is commercially known as the WiMAX. Likewise, in the next few slides, I'm going to demonstrate some of the potential opportunities and challenges of employing one of the most recent IEEE standards to satellite communications. This standard, which is the IEEE 802.15.3D standard, has been released not too long ago, specifically in 2017, to be the first worldwide standard that regulates the wireless communications in the terahertz band. And this standard dedicates about 69 gigahertz of bandwidth for multi-channel signaling in the frequency band from about 250 to slightly over 320 gigahertz, supporting a wide range of data rates from 1 gigabits per second and up to 300 gigabits per second. The usage scenarios defined in this standard cover distances from 50 millimeters to several kilometers. So what could be the opportunities offered by this standard when it comes to terahertz satellite communications? Interestingly, we have found out that the close proximity application scenario defined in this standard could be useful for the rapid and contactless installation of chips and printed circuit boards, which usually exist in satellites. And this is particularly useful for short-term space missions, when the mission time is crucial to the success of the whole trip. Another interesting observation we have found out is that the high data rates defined in this standard could be a perfect venue for high-speed or high-resolution imaging in the live broadcast mode. Also, the high-frequency range, over which this standard is defined, makes it possible to use very small antennas, which resonates perfectly with the size, weight, and power constraints or the SWaP constraints in the design of small satellites. In addition, If you are more interested in the low Earth orbit satellites, the IEEE standard offers the widest bandwidth and the lowest atmospheric loss in this band. And actually, the advantages didn't stop there. It is important to mention that optical, or at least optically compatible technologies, are required for the generation and processing of terahertz signals. And owing to the well-known advantages of optical devices, again, we have more to present to the SWAP constraints. Therefore, our first design goal has been focusing on optical techniques to implement the terahertz signal processing tasks defined in this standard. Further to that, we have been working on simplifying the architecture of optically assisted terahertz transmitters. I'd like to highlight that the IEEE standard imposes some spectral constraints onto every single user wanting to secure a place in the IEEE band, which makes the compliance with this standard a challenging task. In other words, complying with these constraints using the conventional waveforms, such as the raised to cosine waveform and the better than Nyquist waveform, does not allow us to use more than 70% of the total terahertz power that we are allowed to use. Therefore, we have developed a new signaling waveform with a new spectrum that can utilize 99% of the total admissible power limits. To put into perspective, for on-chip and chip-to-chip wireless links, the link distance doesn't exceed 5 millimeters as defined in the IEEE standard. So a 16% increase in the wireless reach means less than 1 millimeter, which doesn't make a big difference actually. However, for inter-satellite links, the communications distance can be as high as 100 kilometers, which means that the improvement can be up to 16 kilometers. An important implication of this observation is that the inter-satellite distances can be increased and the number of satellites required to cover a given range could be potentially reduced. Experimental results show that, indeed, the proposed pulse shape outperforms the conventional pulse shapes in terms of the link error performance, at least for close proximity applications. And a modified version of this pulse shape has been developed as well. And this is to reduce the link error rates under severely low signal-to-noise ratio and high time jittering conditions, as shown in the bit error rate plots and the eye diagrams. I'd like to point out that initially, we relied on a photonics-based Terahertz system at Osaka University in Japan in order to conduct experimental parts of this project. But now, and after 2 years of hard work, we have set up our own system at the University of Adelaide. Sorry if it looks a bit bulky and messy, it's just a prototype for proof of concept purposes, but a real system should be much smaller than this, I can promise. The next thing. In terms of academic research, the project plans to investigate the transmission performance of this IEEE standard in typical atmospheric conditions. I mean, when the standard is employed to satellite to ground and satellite low Earth orbit terahertz links. One more research outcome is a technical report that highlights the role and capabilities of some signal generation and measurement equipment that we have found useful throughout the experimental phase of this project. Also, it is planned to develop a software platform which should be able to generate directly signals that comply with this IEEE standard. So, to summarize, we have identified and overviewed, at least partially, the potential applications and challenges of applying the IEEE 802.15.3d standard to satellite communications. And applying the IEEE standard to satellite communications has its own implementation challenges, as we've seen, due to the unique generation and transmission impairments, as well as the high data rates targeted. And also, conventional waveforms and signal processing techniques must be carefully adapted before being mapped to the terahertz domain directly, in order to cope up with the new challenges introduced in space environments. And last but not least, on behalf of the project team, I'd like to thank the following agencies for their generous support: the Australian Research Council, the Australian Government, together with the University of Adelaide, and the SmartSat Cooperative Research Centre. And here is a list of the peer-reviewed journal and conference publications resulted from this project so far. Thank you very much for your attendance, and should you have any questions regarding this project, please feel free to correspond with me via this email address. Thank you very much.
Yeah, hi everyone. Yeah, thank you very much, Mohammed, for the interesting presentation. Yeah, and I think it's a very interesting. You mentioned 802 15.3 is that's original for the FireMax, right? If my memory serves me correct, it was one of the contending technology or standards for 3G standardization, and lost the battle to the European peers. Now it's coming back for 60. Yeah, looks like in terms of terahertz communication. So I wonder if you do have any comments on this regard, because WiMAX has been there for quite a while. So what do you think this new terahertz component of the WiMAX is going to push it up to the future 60 for potential space utilization? Yep.
Yeah, thank you very much, Farfai. And I fully agree with you that there's some overlap, undeniable overlap between different IEEE standards. And actually, they are just like the same version of previous standards, but adapted to match the requirements and unique challenges of the terahertz band. And actually, this has been the case with many standards. So if we need to go one step back, so it's like an amendment of a previous standard, which has been released also not too long ago, and this standard was specifically designed for millimeter wave communications. So this is the modified form of the millimeter wave standard that I think has been released in 2016. So just 1 year before the release of this particular terahertz standard we're talking about. And with some modifications, and the fundamental modification is the shift in the frequency spectrum from around 30 to 60 gigahertz in the millimeter wave band. I'm not sure if this is very accurate, but yeah, for the IEEE terahertz standard, it's designed to meet the requirements of the and challenges actually of the 250 to 320 gigahertz band. So, and this is not the only modification. So this is just one of the modifications, but there's many differences between this standard and the previous standards. But yeah, we cannot deny that there's some overlap in the definition of the basic parameters and different things. Another interesting thing, or actually more fundamental difference that will not be clear in the technical or theoretical definition of the technical specifications of this standard is the implementation challenges. So, so far, if we're talking about like the spectral constraints, the same waveforms that we used to do a long time ago, redoing or reinventing the same thing, reintroducing the same thing to the terahertz band actually comes with unique challenges. So far, for example, if we need to implement the processing at the baseband, it's not doable. And actually, after some analysis of the standard, we're seeing that part of the standard, actually the standard can be divided into 3 slides. The first slice is much more suitable for baseband processing tasks and these things, which we used to do in previous standards. But the other 2 slices, or I'd say the upper 2 slices of the spectrum or layers of this, of this standard, actually, it will be much better to implement the standard using directly optical components or work directly on the optical domain, or currently we're doing some processing in the terahertz domain, using terahertz components as well. So in terms of the implementation, it's quite different actually. So not all baseband processing techniques are going to be mapped directly from the previous standards to the IEEE standard when it comes to the actual implementation of prototypes and ready-to-use equipment.
Yeah, thank you. Yeah, got one more question for you. You talk about experimentation, and you showed some nice experimental setup in your slides, and I find them very interesting. Yeah, and so here's a question. Yeah, so we all know a lot of the the terahertz channel models is now published in the papers quite theoretical. Yeah, I congratulate you setting up the test bed in your laboratory. But have you considered about doing because in the laboratory you can only do the ground-based communication. Have you considered how to conduct a real satellite to ground base station communication, or even inter-satellite communication? I think that's more interesting, more challenging, because considering
Yes.
the power consumption.
Yes, that's very interesting. So actually, like I said in the presentation and the video recording, actually, we are interested in two quite different ranges of coverage distances. The first one is the close proximity link distances, and where this is more suitable to laboratory experiments and these things. And the other part of the project is more focused on intersatellite links, where the distances are very large and can even exceed 100 kilometers. In this case, this is applicable to intersatellite communications and satellite to ground communications. For intersatellite communications, we have different issues other than the close proximity systems. But what really deserves more investigation and more time to be dedicated to is the satellite to ground communications in the terahertz band. This is what cannot be done in the laboratory. To solve this issue, actually, we have two-step process. I didn't have the opportunity to mention too much detail in this, but it's a two-step process. The first process is to study this using simulations, using the existing channel models and the specifically developed for the terahertz band. And the next step, or actually the second step, and should be the final step, is to use channel emulation equipment provided by the industry partner. So far, this equipment works very well for channel models outside the terahertz band, below the terahertz band, or below 100 gigahertz. So these equipment, I believe, it should be reprogrammed according to the new models of the atmospheric loss and satellite to ground links in the 3 gigahertz band, 300 gigahertz band, so that we can use the same equipment to do some laboratory experiments. And according to some reports released by our industry partner, these channel emulators actually produce very accurate results when it comes to below 100 gigahertz band. So we need to adapt them, but to match the terahertz band. But actually, this step is currently on hold or postponed to the third phase of this project. So this will be the next step to investigate.
Great. Last, it's not a question, but comment. I noticed towards the end of your presentation, you list the outcomes in terms of publication you have achieved. At least I think 1 or 2 publish a very high ranking IEEE journals. So congratulations on your achievement so far, and I'm very confident you are going to progress well. Yeah, all the best. Yeah, thank you again for your interesting presentation.
Thank you very much.
Our next,
thank you.
Now we're moving on to the next speaker, Zaya Valapur, PhD from MIT University. So the topic is a machine learning-based solution for space situational awareness and space sustainability. So Zaya is an engineer by training, and tech enthusiast and futurist by passion. Yeah, very good. And he's hustler, interesting, and trying to harness technology to make it accessible and thereby making the world a bad place to live in. And he has founded a startup which was recognized and awarded as one of the top startups that could potentially change India. He graduated with master's in advanced mechanical engineering from Monash University and is now pursuing a PhD in geospatial sciences at MIT University. And he has developed a mathematical model to assess of collision for current and future objects in orbit, both satellites and debris, as part of his master's thesis, and now is working to better tackle the growing problem of space debris as part of his doctoral research funded by SmartSat CRC. I'm sure I think the space debris is a big problem for the humans and all nations around the world facing. And a lot of us have heard a lot about space situational awareness. And so I think that's a very interesting presentation. So we're looking forward to that. So over to you, Zara.
Good afternoon. Hi, Valapur Reddy. I'm a SmartSat PhD student at RMIT University. Today, I will be sharing my research progress on developing a machine learning-based solution for space situational awareness and space sustainability. The research is supervised by Professor Alison Keeley and Dr. Brett Carter at the university. Introduction. Let's start with what is Space Situational Awareness, or SSA. SSA has no standardized definition, but it refers to the knowledge of natural and human-made residential space objects, or RSOs, in our near space environment. SSA has not always been an integral part of space operations, despite the push from research community. The earliest paper explaining the potential catastrophic scenarios date back to the 1970s. It has become an important consideration only after several accidental collisions and debris creation events, such as the anti-satellite test or ASAT test, space-based collisions, and orbital breakups. The cumulative objects versus time graph shows the green debris spikes in the year 2007 and 2009, caused by the Chinese ASAT test in 2007 and an accidental collision between an operations spacecraft from the Iridium constellation, Iridium 33, and a defunct or retired Russian satellite, Cosmos 2251. The risk to these assets is increasing at an alarming rate, especially with the onset of mega constellations. The orange spike from the graph represents the exponential growth in the number of active satellites, which are our hidden potential future debris. This image on the top right shows the current debris situation in various Earth orbits. Why SSA? To protect our space-borne assets, which form the framework for various technologies that we use today. It plays an important role in ensuring safe operations and to provide warnings of potential natural and man-made hazards. Motivation for my research. Let us start by looking at the current space situational awareness infrastructure. This is a map of the United States Space Surveillance Network, the European Union Space Surveillance and Tracking Network, the Russian Space Surveillance System, and International Scientific Optical Network. Something similar among the existing infrastructure. They're all ground-based. SSA currently depends on ground-based tracking capabilities, limiting the accuracy to trackable objects to 10 centimeters and larger in the low Earth orbit, which is the most crowded of all the current orbits. My research focuses on developing a machine learning algorithm that would be integrated as an onboard computing capability to existing or future space infrastructure to improve its detection capability, bringing currently out-of-scope RSOs of size 1 centimeter to 10 centimeters to within scope. Methodology for the research. Due to lack of space-based data or resources, we have decided to use a simulation transfer machine learning approach to developing the detection algorithm. The flowchart depicts the various stages in the development of the algorithm. The process flow initiates with the utilization of RMIT's Robotic Optical Observatory, in short ROO, to collect the data. The data will serve two main purposes. First, to develop the detection algorithm, and second, to generate simulated space-based data. Once the initial detection algorithm is developed, we will apply supervised machine learning techniques to improve its detection capability. The improved algorithm will then be retrained using simulated data to be able to perform space-borne detections. The final detection algorithm shall be tested and compared to other detection algorithms for evaluation. The algorithm shall be ready to be fine-tuned with any real data to improve the detection capability of the system. Automation capability of the algorithm shall be tested at all stages through true integration to mimic onboard computing capability of the space systems. RMIT's Robotic Optical Observatory, or as we like to call it, ROO. ROO is a 16-inch hammer-viewing design telescope. It is a permanent installation at RMIT's Bandura campus. It has a 16-megapixel monochrome CCD camera that can produce sub-arc-second angular resolution. It can track space debris, satellites, asteroids, and other objects and measure their movements and trajectories. Here is some cool stuff that we can do with ROO. In the video, all the black dots are detected objects, and of the dots, you'll be able to see that there's a small dot which is circled in red, which is constant while the rest of the detections move. This is because we are tracking in a sidereal tracking mode. And as some of you might have already guessed, this is a geostationary satellite being tracked. The video is stitched using 5 selected images with a conformed satellite taken as a part of our observation campaign on 28th of June 2021 and processed through Astro ImageJ. ROO is completely automatable and remote control capable. On 28th of June, we have programmed it to complete a geo search grid where ROO scans the geo belt visible from Bandura, Victoria. The image to the top right is a telescope pointing towards the sky, and the image to the bottom right is Dr. Carter with other researchers at the university. Results so far. We have successfully performed detection of objects and have been able to characterize them. The first image shows the image as read by the code. The second image shows the segmentation used and the objects detected and either characterizing them as either satellite or not. This characterization has already been integrated into ROO operation code to take more images at a point with potential satellite or move on to a different location if none found. This has significantly brought down the time spent and data downloaded at a particular point. We have been able to complete a complete cycle of GeoSearch grid overnight with the adapted code. We have had cases where the code picks up false positives and false negatives, mostly at the border regions of the image. We are performing analytics on the data similar to image 3 at the top right, and are in the process of learning to train the supervised learning stage. Alternatively, we are experimenting a relatively efficient detection code too. To conclude, we have been progressing with the research as planned. ROO's complete remote capability has allowed us to progress without much hassle, even through the lockdowns in Melbourne. We will continue to experiment on the new algorithm and apply machine learning techniques. By training the algorithm through the transfer learning technique and testing the automation capability on ROO, we aim to have the algorithm ready for spaceborne applications. Thank you for your attention, and we'll take questions.
Thanks, Zai, for the interesting presentation. From on the situation awareness and space sustainability. I find it quite interesting and just one of the family topics. I've noticed. Got a question for you, Zai. I've noticed you mentioned in terms of you want to use machine learning to apply technology. You mentioned the transfer learning. So the questions about the transfer learning, sometimes, when you transfer neural networks from a different application to the current one, and it doesn't work, and either you have to significant change the architect, or there's a lot of trouble goes into, fine-tune the parameters. So I wonder, what's your experience so far? Because you've already presented some results. So have you encountered such problems?
We haven't encountered any such problems so far, but I've looked into some previous papers which have mentioned the issue that you have asked. So as of now, we have not encountered, but we are anticipating at some point we might, especially when we plan to use simulated data, which is our next step after machine learning, initial machine learning. So to overcome that, so one of the problem with transfer learning is the exact path that we want to transfer when we want to do it. So it's like one of the most common example I use when we need to explain transfer learning to someone who has no experience in algorithms is, it's like learning to drive a push bike and using skills that we learn from the push bike to drive a motorbike. So there's only some particular specific skills that we can use when we want to use a motorbike, right? So we don't know how to use the gear system or the acceleration, but the balancing which we have learned from the push bike can be completely transferred. So as long as we are focused on using the specific parameters, the chances of that those errors coming in might be significantly lower. But yes, it's going to be an on-the-go basis, and I am anticipating we might run into this at least once while I keep improving the algorithm. I don't have an answer on how I might overcome it right now, but hopefully I might be able to answer it better when we do it.
Yeah, thanks for answering that question. We have another one for you. Yeah, so would using a network OS sensors improve the performance? And any other detections on the sensitivity or position accuracy? Yeah, can you use that to improve both performance, detection sensitivity and accuracy? Can you have a comment on this?
We have considered using sensor fusion as an added layer, but we haven't experimented with it so far. So once we go to a point when we can actually, we have not yet come to a point where we have actually applied machine learning techniques or completed the detection algorithm so far. So once we do it, we might consider sensor fusion as an additional improving capability.
Good. Yeah. One more question for you. Yeah. So what are the key challenges or differences going from ground-based to space-based, and what are you doing to train and test for that?
So yeah, good question. That's in fact, I struggled a lot with this particular question because there are quite a few contradicting research outputs in this area. Sometimes some research outputs show that ground-based sensors might detect RSOs of lower magnitude than space-based systems. And some research say that actually space-based systems might be better because especially like from my understanding, it depends. It is a bit more complicated than that. It depends on the way. So if we are looking at sunlit regions, or if we are looking at it depends on from first space-based situation. It's like if you're looking at sunlit regions, or if you're looking at when both the objects are in the shadow of Earth or any other penumbral or umbral regions. So it's a bit more complicated. I might not be able to give an exact insight, but we are still pursuing into what might be. At first, when I started the research, I always thought space-based might always be better. But I've seen research outputs where some researchers have shown that ground-based might give some capabilities which space-based might not. And honestly, the way forward might be using both the data together through a sensor fusion capability, similar to what US has experimented. So in fact, one of the recent developments that we have done is we are participating in SACT exercise, and we are trying to upload the data that we get from RMIT RU into the UDL, which is maintained by US Space Force or one of the US military things which actually does active SSA and feeds data into SpaceTrack. So I think distance of fusion might be a way, and using best of both the worlds and ground-based detections and space-based detections might be the way forward.
Well, Zara, I can see people really like your presentation. I have 2 more questions for you. So please keep your answer to be concise. So the next question is that you mentioned at the beginning of your presentation, the ground-based system will not be as effective in detecting anything less than 10 centimeters in diameter. Yeah. So the question is, have you tried to push the limits of ROO in terms of object resolution?
Sorry, I did not get the last part of the question.
So the question is, have you tried to push the limit of ROO, the facility at RMIT, in terms of the object resolution?
Yes, we are currently pushing the limits while we are working at various experiments. As so far, we have been able to detect objects as small as 10 centimeters, which is 1 CubeSat. We have been able to successfully track them. Sometimes one of the biggest problems when we are trying to push the limits is there might be some anomalies which we don't understand, and we are trying to categorize them. And the way we are doing it is we are working on, so other than the machine learning, computer vision based machine detections, we are actually looking all the images that we collect and analyze to categorize them, and we are in process of pushing the limits.
Great. Yeah. So last question is not a question as such, but a helpful comments from Peter Kerr to help you. Yeah. So here's the information he want to pass on to you. So Canada launched a LEO satellite imaging at the geo belt a number of years ago. It was called Sapphire. So this might provide some space-based imaging data. And perhaps we can help you with MDA, can help you with obtaining the data if that's possible. So if you're interested, you can further get into touch with Peter. Yeah, I think that's very
absolutely
helpful.
Absolutely, that would be great help. I will get in touch with Professor Peter Kerr, and yeah, I will do that. There were a few satellites which were previously operational in the space-based regime. And any data would be helpful, honestly.
Yeah.
We have
Great.
tried, but we were not able to get our hands on it so far, but looking forward to it.
Yeah, great. Thank you very much, Azar. Yeah, and not only for your presentation, and also you handled 5 questions from the audience. Well done. Yeah.
Thank you.
So our last speaker before the break is Zaraki Orr from La Trobe University. So his topic today will be using blockchain and DRBs to orchestrate on IoT network. So Zaraki is a PhD candidate at La Trobe University, Melbourne, and currently he's working on blockchain applications and research in the IoT space. Zaraki's research is focused on applying distributed consensus mechanisms at the fork layer of IoT networks, with the purpose of reducing the dependence on centralized architect. So the aim of his PhD research project is about applying the framework to wireless sensor networks and to move data processing and authentication from the cloud layer up to the fork layer, or should I say down to the fork layer. So Zach completed his undergraduate degree at La Trobe University, and also he did his computer system engineering honors degree at La Trobe. And during his honors year, Zaraki has developed a framework called FOOSA, F-O-O-S-A, and that is able to provide API to simple development in software-defined networking at the application layer. So over to you, Zaraki.
Hi, everyone. My name's Zach. I'm a PhD student from La Trobe University in Melbourne. And today I'm going to be talking about how we can use consensus mechanisms and blockchain to secure IoT networks. Almost 3/4 of organizations hosting data or workloads in the public cloud experienced a security incident in the last year. 70% of organizations reported they were hit by malware, ransomware, or data theft in the last year. This is a report compiled by a well-known antivirus vendor. And as we can see from these figures here, cloud security is really hard to get right. and even among the likes of Facebook and LinkedIn and Twitter, it's really hard to get the security right. Even most recently, Amazon's streaming service Twitch also had quite a large breach where a lot of their source code was leaked and a lot of confidential information like the earnings of their content creators was also leaked. And now I'm going to be getting into why this issue with cloud security really affects IoT devices. So IoT devices are growing really, really quickly. We had a few billion devices towards the end of the 2000s. And now we're going to be looking at somewhere between 10 billion and 100 billion devices at the moment. And a lot of these devices are going to be really dependent on the cloud. And another one of these issues is privacy. So we know that these devices are often placed in sensitive areas like our bedrooms, our kitchens, our living rooms, our offices. And a lot of these devices are dependent on the cloud, thus they need a continuous internet connection. And with this continuous internet connection, they also got cameras and microphones, with the microphones usually being turned on and listening all the time for that "Hey Google" interaction. So why should it be the norm that we just automatically trust these centralized cloud providers to have all of our data straight away? Some sort of decentralized alternative would be better, in my opinion. The other issue I have is a lot of these devices not being future-proof. So a lot of these devices are made quickly, they're iterated on quickly, and they're pushed out onto the market. And a lot of them have or can have a short lifespan. And part of the short lifespan being that online services that they need for a lot of their functionality to work, like text-to-speech, notification, motion sensing and video streams, might be stopped. And if all of these services are stopped, these devices may not be even usable anymore. They may be essentially bricks. So what happens if manufacturers shut down or these devices hit their end of life? They're basically e-waste at that stage if some of these services are stopped. On the left, we've got a picture of how IoT networks were designed in the early 2000s. So usually a company would either host their own infrastructure or they would have another smaller provider host this infrastructure for them. Today, we're a little bit more open. However, this openness is mainly dominated by the likes of Google, Amazon, Microsoft, Alibaba. There's a few smaller providers like Linode, for instance, but it's mostly dominated by only a few players. And 2025 and beyond, that picture there, this is what I'd like the IoT to look like in the future. So rather than relying on this central server, this central company to maintain these services, it'd be better if these devices kind of spoke to each other to make this sort of decentralized network, so we're not really reliant on one central party. And on the right in this triangle, the bottom of the triangle, the technology principles, I'm striving towards, with my research, designing peer-to-peer systems for those IoT networks to talk to each other. I'm looking at doing trustless communication between these devices, and I'm also looking at researching decentralized autonomy. Briefly, I'm just going to go through blockchain and consensus, so we're all on the same page. So a blockchain is a data structure where each block is cryptographically linked to the previous block. And what I mean by cryptographically linked is we take a hash of all the information of one block. So we make this, this string that identifies the block, gives the block a unique fingerprint. And then we can embed this unique fingerprint in a block in what's called the previous block hash. And then whenever someone tries to tamper with a block or change a block, either maliciously or by accident, it's really easy to see if anyone's tried to tamper with the history of the ledger. And the blockchain is well known for being used in Bitcoin. And the blockchain is just a distributed data structure that allows anyone on the Bitcoin network running a full node to be able to verify transactions on their own and verify Bitcoin's consensus rules on their own without having to trust another party to do this for them. So we probably know intuitively what consensus is. It's just a group agreeing on something. So people, it might be a group of software systems, it might just be a group of electrical systems. And in this example, these people are going out for dinner and the group decides they want pizza. They've come to consensus that 3 of them want pizza and they've overruled that poor person that just wants burgers. But a more practical example could be on an aircraft where we've got all these electrical systems all talking to each other. And some aircraft use a system called Byzantine fault tolerance, where if one part of this electrical system fails, it's not going to take down the other systems in the airplane. So Byzantine fault tolerance is really important for systems that provide critical infrastructure or that need to keep working even if a small part of the system fails. So what's so important about Bitcoin, the blockchain, and why is Bitcoin's consensus mechanism unique? So consensus was a pretty hot research topic in the 80s, the 90s. It sort of died down a little bit in the 2000s until Bitcoin was released. And Bitcoin could guarantee 2 things that a lot of other consensus mechanisms couldn't. So one part is, can you provide consensus with irrational actors, specifically Byzantine actors? And the other part of this is, can you continue providing consensus guarantees in an unstable network, or otherwise known as an asynchronous network? And where a lot of these consensus mechanisms couldn't meet these 2 criteria, for some reason Bitcoin could. This is because Bitcoin made an interesting trade-off between liveness and safety. Briefly, I'm just going to talk about my research and how I've structured it. So the first part of my research was basically my own study for myself to learn about all these topics. So I looked at IoT, distributed networks, I looked at Bitcoin, blockchain, P2P protocols, all those sorts of things. And then using this knowledge, I made a proof of concept consensus mechanism. And then I did some testing on the consensus mechanism and I found it wasn't awesome. So my third research question is, how do I improve this consensus mechanism? Specifically, one part I'm going to be looking at is how can I improve the distributed key generation algorithm, and how can I lessen the impact on some of these bottlenecks that IoT devices have due to their constrained processing nature. And the fourth part of my research is going to be looking at how can we validate data on the IoT devices that's coming, that they're generating, so their time series data. How can we look at it and say, this data is valid or this data is not valid? I'm going to be doing a bit of research into how we can do that with machine learning. So this is how my consensus mechanism is going to work. Basically, the first part of it is a P2P network. We need all these nodes to be able to talk to each other without a central party brokering this interaction. The second key component is the threshold signature scheme. Threshold signature schemes such as the BLS threshold signature scheme allow us to take these, multiple cryptographic values, hundreds, thousands, maybe tens of thousands, millions, depending on how much processing speed we have, and then aggregating them into one aggregate key. So instead of having to check hundreds or thousands of these signatures or keys or private keys, we can just check one because we've aggregated it together. And the last part is secret sharing. Secret sharing involves taking a secret piece of data, splitting it among a bunch of nodes, and then having a rule where maybe 50% or 75% of these nodes need to come together in order to recover the secret. And using these mechanisms, we can create a lottery leader election system, or more simply, a distributed pseudo-random number generator. And the point of having this random number is so on this network, we can give our peers particular roles. These peers might be required to join the committee, which is a particular function used in POS consensus mechanisms. We might even require them to be a block producer or just to witness what's happening, or they may be inactive. So this random number is used to give these devices jobs in our network. So what's the point of this? So the point of this is that instead of having this central rule enforcement, we've got these nodes checking the rules for themselves, checking the consensus rules for themselves, and validating them themselves rather than relying on a central server or party to do this for them. Thanks everyone for listening, and I'll answer your questions now. Thanks so much.
only have a time, to ask you a quick question, and please keep your answer concisely under 2 minutes, preferable. Yeah, very quickly.
Sure.
The question is about, you mentioned about pushing the data processing, the blockchain algorithm, on the IoT devices from the cloud layer to the fog layer. So have you considered about, many or most of the IoT devices are battery operated? Yeah, so the power constraint is a big problem if you push that down to the fog layer.
Of course, yeah, we can only do so much. At the end of the day, it's the IoT, so we don't really have the processing power here to do heavy machine learning or heavy calculations or those sorts of things. What I'm more aiming for is more decentralized autonomy, where rather than relying on like a central command and control server to issue commands to these devices or to issue or to keep these devices in sync with each other, I want them to more do this in a more decentralized manner. So it's probably less about doing the processing and more about the control and the autonomy that a consensus mechanism could add to maybe a series of satellites or a series of UAVs that all have all these little embedded IoT devices in them.
Thank you, Zach. Yeah. So, and hi, folks. This concludes the part 1 of the PhD presentations. So we're gonna have to shorten our break from 10 to 5 so that we can catch up time. Yeah. So I will see you guys. Enjoy a break, and I'll see you guys in 5 minutes. Thank you.
No, let's just leave it as this. Okay, 5-minute break now. Thank you very much to Wei and the presenters in the session. See you back.